Hi, so welcome to my first ever video. We'll be solving the 2019 International Math Olympiad, problem 5. So, I chose this problem because, I guess it's like the only Math Olympiad problem that I've ever been able to solve, but also because I think it has a really, cool solution. So, basically what we have is we have these coins, these N coins, right? And like all in a row. So we have like N coins, H, T, H, T. And we just do this operation where we have a certain number of heads. So here we have 3 heads. And so 3 heads. And then we go to the 3rd position because we have 3 heads. And we flip this guy. So this becomes head. Right. And then, so now we go back. And this becomes H, T. And now we say, now we just do the process over again. So now we have 4 heads. And then, we take the 4th, the coin in the 4th position, we flip it, and we just keep doing that. So part A asks, is this sequence ever, will it always stop? Yeah, so will this stop at some point? Okay. So that's part A. And then part B asks the expected value. So we'll get there first. So part A, what we can do is essentially proof by induction. So we're going to have a couple base cases. So n equals 1 is the first base case. So if we have an h, this just goes to tail. And now we're done. And if we start with a tail, well, that's it, right? Like we're done. There's nothing to flip. Okay, so for n equals 2, there's 4 possible configurations. So HH goes to HT, and that goes to TT. So this part is a little bit tedious and not very insightful. So this goes to TT, TH. This goes to HH, which we already know goes to HT, and that goes to TT. And then finally TT stops. So that's our 2 base cases, and then we can prove by induction, right? So we have an inductive hypothesis. So we're going to assume, so by the inductive hypothesis, we're going to have some sequence of length k, and we want to show if this terminates, so we assume this terminates, assume a sequence of length k terminates, right? We have to see whether or not a sequence of length k plus 1 terminates. So what we can do is, okay, so by the inductive hypothesis, we know this terminates. So what does something, a string of length k plus 1 really look like? Oh, so we have something of k minus 1, or k, and then we add in, we can add a t at the end. But if we add in a t, we say that when we add a t, we see that this will never change to heads. Never change to head. So why is that? Well, so like worst case scenario, like all of these are h's, right? All of these are h's. So we have kh's. So then what we flip is this one, the one right before the t. So this t will never get flipped, even if we have all h's here, right? So this will never change to h. So if it ends with a t, it terminates, right? We're good. It terminates, right? But so, because we're using the inductive hypothesis here, and then we have a sequence, and then we have something where it ends with an h, and we want to say, does this terminate, right? So, so we already know if this changes to t, right? If this changes to t, we're good. We know the sequence will terminate because then it reduces to this above case here, right? So we want to show that this will always switch to t, right? We want to show this changes to being a t at some point. Okay. So, how does this happen? Okay, so we can assume by contradiction that this always is a t and never changes to h. Or it's always an h and it never changes to t, right? So we assume by contradiction this is always an h. So basically what that means is that this never flips. So we can never have a case where we have a bunch of h's, right? We have k-h's here. K-h's. And then a final h at the end. So if it's always an h, this can never happen. So the question is, can this happen? And if this can happen, or if this is certain to happen at some point, then this is false. Then this will change to a t, right? Okay, so how do we know that? Okay, so by the inductive hypothesis, right? We know that at some point. Okay. So this is a little bit tricky, but what we're going to do is we're going to look at the first coin flip here, heads or tails. So we can have h k minus 2 of something, and then an h, or we can have a t k minus 2 of something, and then another t. Basically, what we want to do is, so we want to show here that this can't happen. So let's think about this k minus 2 here. So think about the k minus 2. So we use strong induction here. Use strong induction, and we see that by the inductive hypothesis, at some point this k minus 2 sequence is going to have sorry, this should be an h. So by the inductive hypothesis, this right here is eventually going to become all t's. right? And we know that because we have one H here, right? And notice this first T is not part of the subsequence in here, right? So we always have this one H. So for all intents and purposes, we can kind of ignore this H, but ignore this T and ignore this H, right? Because will always be that this H kind of gets us into the subsequence, and then we can just look at the subsequence, and by the inductive hypothesis, we know that these are all the T's. And then at that point, we have T, we have K, we have a bunch of T's, and then an H, right? So what happens after this? So this is going to become H, and then a bunch of T's, and then an H, and you can kind of see we're going to like eventually get to H, all H's, and then this last H is finally going to change to a T, right? And then that reduces to the first case, which we already know terminates by the inductive hypothesis. Okay, so what about the other case we have to look at? So in the other case, we have this K minus 2, where we have an H, starts and ends with an H, and then K minus 2 of something in here, right? Okay, so now what we can do is, right, so it starts with an H. So then we can look at this subsequence here, ignoring the first H, right? Because if we're assuming this is always H, then this H here will always be ignored, right? So assuming we always have this H here, this first H will never turn into a T. But again, this is a subsequence here. So by induction, by the inductive hypothesis, we know that all of these, eventually all of this will become all T's, right? It will become all T's. So then we're back to the first case, which we know this case here, and by the inductive hypothesis, we know it terminates. So we've covered all the cases, and we are done with part A. So now we can move on to part B. And so this is the fun part. This is where we use the most beautiful idea in all of math, which is called symmetry. Right? So this is how we're going to compute this expected value here. Okay, so we're going to define some notation. So we say L of n, right, sub n. This is going to be the expected value of a sequence of length n, right? Okay. So similar to before, we have two cases. We have some amount of, we have these n-1 coins, and then we can end with a t, right? And again, this t will be ignored, right? And so these count for 1/2 of all configurations of length n, right? So what we can write is L of n is 1/2. So this is L of n-1, right? L of n-1. So we have this recurrence relation here, right? So the question now is what will go here. So in other words, what about the case where we have some stuff and it ends with an H, right? What's going to happen here? What's going to happen in this case, right? So as before, we want this H here. We want this H here to turn into a T. Because once it turns into a T, what happens? So as soon as the minute this changes into a T, right? In order for this to change from H to T, we need to have all H's here, right? All H's. Because in order to change the last one, all of these need to be H's. So if this changes to T, then we have this string of n-1 H's, right? And then you can kind of see that on the next iteration, this will become T, the next one will become T, next one will become T, ... and so on, right? Okay, great. Okay, so now the question is, we have these n-1 H's, right? So how long does this take these n-1 H's on average, right? How long does this take to get there? And this is where we will use the idea of symmetry. So we have so we're going to consider all so consider all configurations of length n-1, right? So there was going to be a one-to-one correspondence kind of like an automorphism, if you will. So this is going to be so let's define that we kind of define this informally, but there was going to be this automorphism on the configurations of length n-1 that basically switches all of the values, right? So if n-1 has length 4, this configuration is in one-to-one correspondence with we just relabel all of the T's by H's and H's by T's, right? And now what we can do, ready for the magic, is once we have this correspondence established, what we can do is say, okay, under this correspondence, where does this go to? This goes to all T's, right? All T's. So now, what we can basically see now is under this one-to-one correspondence, we make a new game, right? Where instead of flipping, so notice if we have k heads, this is going to give us over here we're going to have n-k heads. In other words, we're going to have k tails, right? And we can play an equivalent game in this kind of like the image of this automorphism here. We're going to play a new game where we instead of flipping, right? Instead of counting the number of heads, right? Instead of counting the number of heads, we count the number of tails in the configuration. We count the number of tails, and then we flip that, right? Because the tails over here and again, 1-to-1 corresponds with the heads over here, right? So basically what we have is, so notice we have L of n, right? So let L prime of n be the expected value of this new game over here, right? Well, we can kind of see easily that L of n is equal to L prime of n because of this, because we're kind of playing equivalent games and we have this 1-to-1 correspondence. So this is really the nice step. So what does that mean for us? So that means for us that, okay, so on average, right, how long does it take to get to this place where we have all heads, right? Well, on average, right, it takes the same amount of time as it does to get to all tails, right? If we play this make this transformation and play this equivalent game over here with tails instead of heads, right? So essentially, what this is saying is that in order to reach this stage over here of this n-1 heads, this takes precisely, on average, this takes precisely L of n minus 1 to get to all heads here, right? And we know that after this, we need n more, right? This changes to h, and then we get, it changes to h, and then we get a bunch of t's, right? So we need n more steps to get here. So this right here is what fills in the question mark. It's what fills in the question mark. Up here. Fills in this question mark. So now we just have this nice recurrence relation. L of n is equal to half of L of n minus 1 plus a half of L of n minus 1, and then in parentheses we just expand. We get this, right? And this here is just L of n minus 1. And if we solve this recurrence relation, which you can kind of do by inspection, it's not very hard, right? You just get that it's n plus n times n plus 1 over 4. That's your answer, right? And that's how you solve this using symmetry.